Hello! In this video we're going to look at how to structure a proof where we need to make conclusions from quantified statements. So the quantified statements will appear in the assumption lines, and we want to see how we can draw conclusions from there. Or maybe they don't appear in the assumption line. Maybe one of the conclusions is a quantified statement, and we want to see what further can be concluded from that. The example we're going to work on to illustrate this type of situation when setting up a proof in bracket notation is the following. We're going to prove the theorem that states that if for every x there exists a y such that x plus y equals 0, and at the same time for every x x plus 0 is equal to 0, is equal to x and is equal to, and also 0 plus x is equal to x. But actually we're only going to make use of, we're going to make use of both. 0 plus x equals x. Note that there are hidden brackets here. There should be brackets around this and around that to distinguish it from the end. So in other words, to evaluate this first before we take its conjunction with the other one, and the same for the other one. So if we have that and that, moreover, if we also have that for every x, for every y, and for every z, x plus y plus z equals x plus y plus z, then out of all of this we can draw the following conclusion. So what I'm going to write now is an implication. So all of this together implies that for every x, for every y, and for every z, x plus y plus z equals x plus y plus z. So our theorem states that this very long statement implies the other one, and altogether we get one quite long statement. And you can imagine the proof will be long as well. Okay, let's make a few remarks before we get started with the proof. And maybe also introduce some abbreviations to not to have to write out long things over and over every time. So the first thing, the variables, as we've agreed, we have to, every time we set up a mathematical language, we have to have some kind of intuitive understanding what kind of objects do the variables represent, and also some kind of intuition for the special symbols used in that context. And from what we see here, we might as well think that the variables represent the numbers, and the plus there is the usual addition of numbers, and 0 is the usual number 0. But in fact, our proof will not depend on this representation. We're not going to make use of any facts about numbers, anything at all. We're going to use none of them. to prove this theorem. So it means that the variables could have been any kind of object we like them to be, as long as we have some kind of functional symbol plus defined for them, and that could have been anything at all as well. And another functional symbol 0 here, which is a constant symbol, it gives us an object called 0, and that could have been any object at all. And the theorem still is going to work. Just to give you one other example of possible interpretation for this language would be where objects are, let's say, just the positive numbers, and the plus is multiplication, and 0 stands for number 1. Then the same theorem would still hold. Of course, with the now as I'm talking, I'm realizing that I wrote nonsense, so I apologize for that. What I meant to write here was not the same thing as I already wrote there. That was not my intention. What I meant to write here was x plus y, actually x plus z, equals y plus z, implies y, and again I made a mistake. I wanted to write there, no, that's fine, sorry. That implies x equals y. So once again, there are invisible brackets here and there. And then one extra bracket is missing here. There we go. Now, if we look at this, if we look at this conclusion we want to draw eventually, you will see that with usual interpretation of variables as numbers and plus as the addition of numbers, we clearly have that whenever x plus z is equal to y plus z, x will be equal to y, because we can just subtract z from both sides of the equation. And of course, the fact that we can subtract z from both sides of the equation is kind of due to this, which kind of introduces subtraction, because it says that for every number there's another number which subtracts it to give 0. And then we will see in the proof that we actually need not just this property but also these two other properties in order to really be able to conclude this from the availability of kind of subtraction given here. Okay, so intuitively, in the interpretation of numbers being the variables and plus being the usual plus and 0 being the usual number 0, in that context, what we're proving is something that is not too surprising for us. And the same goes for multiplication, by the way. If we just deal with positive numbers, then for every number there will be another one such that x times y is equal to 1. Remember, in that context, I said 0 should be the number 1. And so there, it's basically the multiplicative inverses, that's how they're called. And so this is the reciprocal of each number, right? And we can use them to conclude that if x times z equals y times z, then x will be equal to y. So easy stuff. And we choose an easy example deliberately, well, at least it's easy in the specific context where we are more familiar with these things, to see how we can set up a fully featured, precise, complete mathematical proof in the bracket notation. Now, in order to make life a bit easier for ourselves in terms of not having to write long statements over and over again, we're going to introduce some abbreviations. We're going to abbreviate this thing as alpha xy. We're going to abbreviate this thing as beta x, that thing as gamma xyz, and this last one as delta xyz. Just to emphasize here, alpha xy is not a sentence, it's a formula because it has three variables. In alpha, x and y are three variables. Alpha says something about x and y. The whole statement here with the quantifiers is something different. There, the variables are not free anymore. That sentence says for every x there is a y such that alpha xy is true. But alpha xy on its own does not talk about x being arbitrary and y existing for the x. It does not talk about that at all. Okay? And the same remark a similar remark applies to beta and to gamma and to delta. With this abbreviation, our theorem becomes a bit shorter. The theorem then says for every x that exists y such that alpha xy and at this stage, actually, I don't have to use these brackets. We can think of them as hidden brackets because the quantifiers take precedence over the conjunction. So and for every x, beta x, and for every x. And so let me also show you one other abbreviation, or maybe I shouldn't at this stage. We could have written out this instead of having three quantifiers there, we could have just have it written out this way with commas between the variables, but let me actually not do that for now. So this is supposed to imply that, and here we do need the brackets not to confuse which operation is done first, the conjunction or the implication. There is no rule as to which should take precedence over the other. So then we do need brackets there. That should imply for every x, for every y, and for every z, delta x, y, z. And let's see how far we can get by not having to recall yet what alpha, beta, and gamma are saying specifically. At some point, in fact, quite soon, we will need to expand what they say. But for the time being, let's try to work with the general alpha, beta, and gamma, and delta so that we can keep things short. Okay, so in terms of formalizing the step of introducing these abbreviations, the way you could set this up when you're writing this out and want to present it kind of in a neat way would be the following. You say proof. Although you say proof, you're not yet really starting with a proof. You're first introducing some notation, and you're going to say let alpha, or rather like this, let alpha, beta, I mean this is just one way of doing this, right? You could also do it in your own way. Let alpha, beta, gamma, and delta represent the following formulas. And then you explain what they are. So, and you can do it like this. Alpha will have two input variables there, so alpha x, y. And then instead of using the equality sign, because the equality sign also is used inside the formulas, and so not to confuse the equality between terms, in other words, the equality of objects, and the equality of statements, we're going to use, instead of equality, we're going to use colon, as if like, it's like in literature or in English like this colon here. So it's basically saying alpha says, and then let's see what alpha says. Whatever alpha says, that's what alpha represents. Okay? So alpha says x plus y equals 0. And then beta says x plus 0 equals x, and 0 plus x equals also x. That's what beta says, right? And then we have gamma saying something and delta saying something. So gamma says that x plus y plus z equals x plus y plus z. And finally, delta, what does delta say? Delta says x plus z equals y plus z implies x equals y. After you introduce these abbreviations, then you can say we must prove. And so what you've done now, you've rewritten what you were supposed to prove in the shorter form thanks to these abbreviations. And at this point, you can start proving it. So we could add here a sentence saying, here is a proof in the bracket notation, and then display the proof. But let's first work this proof out. All right, so we might need more space than the screen would allow. So let us actually make everything a bit smaller. I think things are still visible here. And let us work out the proof on this right-hand side so we can easily access the left-hand side as well. And then eventually we can copy-paste this and put it under. So if you're working on a paper, this is like doing the rough work. Okay, so what you want to do, of course, you want to put this as the last line of your proof. So your goal is to reach here based on some steps, starting out with no assumptions. And I am assuming that you've watched the other video, which was the first one on structuring a bracket proof, so that you already have some understanding of how this works. So the understanding that's required from the other video, I'm not going to remind you of that. So we want to reach this line. So if you haven't watched the other video, please watch that one first and then come back here. We want to reach this line. And now let us look at the hierarchy of the logical symbols through the directed graph that we also introduced in the other video. So the outermost logical operation that's taking place here is the implication, right? We've got something implying something else. Then the implication takes two inputs, and the left-hand side of the implication is a conjunction of three things. We, in the video where we introduced these symbols, we introduced conjunction just for the two statements where there are two inputs, but the conjunction written this way out is similar to the one for two. So here it takes three inputs, but the interpretation is similar. You want all three of these statements to be true in order for the conjunction of the three to be true. You could also break this up by introducing further brackets here, like for instance putting brackets this way. Then you could use the binary conjunction we already know about and then further conjunct it with the other one. So maybe for the sake of completeness of our presentation, maybe that's what actually we should do. So I'm going to think of this as two binary conjunctions nested into each other. And so the first one takes, so this conjunction I've drawn here is now this one over here. And so it takes the input, another conjunction in the first position. And in the second position, you see, that's this for all x, for all y, for all z. So we've got here for all x, and then we have for all y, and then we have for all z. So we are going into this formula now, and eventually we encounter gamma. So now here we have gamma of x, y, z. So let me just write gamma there. And I'm not going to expand gamma further, because if you remember from the other video, the next step of gamma wasn't really helpful in structuring the proof. It is this one where we use the basic logical symbols that make sense to separate in a picture to show us how the proof should be structured. Of course, eventually you wouldn't have to do something like this. You can immediately start doing the bracket proof structure for this without having to write this out. Somehow your mind will kind of automatically in subconscious level be able to do something like this. So this conjunction, the left-hand side one, has two inputs. The first one is for all x, and then after that we have there exists y, right? And then after that we have alpha. Whereas this one, the other one, has for all x also. And then we have beta. And now let's look at the right-hand side of the implication. So this one, that one has a similar structure to the right-hand side of the first conjunction there. So I'm just going to copy this. But except that instead of gamma, it finishes off with a delta. There we go. And now I just have to replace this one with a delta. Okay, so that's not a very beautiful delta, but hopefully you will forgive me for that. Okay, so we've got now the proof structure in this tree notation, and I haven't used those arrows anymore because kind of I'm thinking of going downwards as the direction of the arrow, so I don't have to indicate the arrow. And now this will help us to see what to do here. So the first thing we want to do, as always, we want to get rid of the topmost node, right? We want to take this off. So we want to kind of already put a framework, kind of template for the proof structure, which will take care of this step in the proof. Okay, so how to do that? So what we're doing here on this side of this tree is that we're basically saying our statement says one thing implies the other. And so to prove that one thing implies the other, we have to assume the one thing and conclude from it the other thing. So then it's quite clear that the outermost part of our proof, so the beginning and the end, will look the way I'm setting it up now. So we'll have a bracket here because that very first line, eventually, through some steps of applying some logical rules, we have to get to that conclusion. And if we do, then we can step out from that bracket, from this assumption, and say, aha, we've shown that assuming this gives us that. So whenever this is true, the first one, then the second one will be true. And that's exactly what the implication says, right? Whenever the left-hand side is true, the right-hand side must be true. And we would have demonstrated this by pure logic, proving that the truth of the left-hand side does logically, in a sequence of steps, imply truth of the right-hand side. Now there are two different directions we could take, given by these two different nodes. So we've got now two nodes, right? So the conjunction node and the for all x node. And so we could either first do something about the conjunction node and take that off from the picture, or do something about the for all x node. And it doesn't matter in which order we're going to do this. So kind of work from the top or work from the bottom. Remember that the top, we're viewing this double conjunction sequence into grouped, to kind of being grouped like that, where we've got conjunction of these two things, and then that whole thing is being conjuncted with the other one. So we could either draw a conclusion from this conjunction, or we could see how we could get to a conclusion which starts with for all x. And let's actually do both things at the same time. So to get to this eventually, we will have to, and this is something we already know from the previous video, right? We will have to assume that we are given x, and from that we should be able to conclude delta x, y, z. So that will take off, sorry, not delta x, y, z, but for every y, for every z, delta x, y, z. For for every y, for every z, delta x, y, z. And that would take off this part here. Now at the same time, we can make use of this conjunction and conclude from it two things. On one hand, this thing, because you see, we're told that conjunction of two things has been assumed. And what does that mean? That means that we're assuming that both of those two things are true. And if they're both true simultaneously, then they should also be true separately, right? So we can then make this as a conclusion. And it doesn't matter in which order do we take them out. Okay, so we've made some progress, right? What we have now on this side is that we've separated, so we kind of don't have to worry about this anymore. We now have three ingredients at hand. These two, and this one, where the first two are on the assumption side. Remember, these are things we'll manage to get through. So if we count these line numbers 1, 2, 3, we can make 2 as a logical conclusion from 1, and we can make 3 as a logical conclusion from 2. So we want to now proceed further, eventually get to the destination, right? And in that process, we can now assume, we now can use the fact that 2 is true and the fact that 3 is true, because they are true under the assumption of line 1. So that's why I'm saying that these two things, which actually represent the whole statement. So line 2, let me be a bit more specific here. Line 2, the statement on line 2 is that whole thing here, right? And the statement in line 3 is this whole thing. And these two statements can be used in our logical deduction to make some conclusions from them, and eventually we want to get some conclusion that we want, but let's not worry about it now. Okay, so on the other hand, this is the thing we want to conclude, but that we can only, and we should only conclude under the assumption that we're already given x. And so I can make a bit more space here and do something similar to for every y and for every z as I did for every x. There we go. In this way, I have eliminated now all of these. We could further eliminate this one by writing out separately the two parts of the second line. So let me add more space here. You see, this is why we do need this to be rough work, because we need to add and space all the time. So in line 4, we could have them written separately. So for every x, there exists y such that alpha x y, and line 5 could be for every x, beta x. Okay, now let's make a few remarks on this. First of all, you see how useful it was that we introduced these abbreviations. Otherwise, we would have to be writing out this long line here over and over again. Huh? Secondly, not just this one line, but so many different lines for each alpha, beta, and gamma, and so on. Well, actually, there's no so on. That's just alpha, beta, and gamma. But also for delta. We've already written out delta 4 times here. Okay, great. Now, second, the second thing I want to say now is actually a question. At this point, where are we in the proof? So to say, how much have we proved? You see, at this point, we are right here in the proof. Now, why am I drawing this line? What does this line stand for? This line stands for the point up to which the proof has already been confirmed. And we don't know yet how to get the next line from all the previous lines. So let's explain, let's see how do we know how to get all these lines from 1 to 8. Line 2 we got by line 1 because of the conjunction. Line 3 we got from line 1 again, right? Line 4 we got from line 2. Line 5 we got from line 2. 6, 7, 8, we don't have to justify them because they're just assumptions. And you see, we are here at this point in the proof. Remember, a proof is a sequence of statements where every next statement, unless it's an assumption, should be a logical conclusion of the previous statements in the right scope of brackets. And all these lines 1 to 8 fulfill that. But we don't know yet how to get to the next line, right? If we knew how to get here, if we knew how to get to the next line, the one right after the yellow line, then all the rest is also fine, because imagine we know how to get this line with the delta. Then, since we've assumed we're given z, an arbitrary z, and we've proved that for arbitrary z, delta x, y, z is true, we can conclude that for every z, delta x, y, z is true. And then the same argument repeats over and over for y and x, eventually to get here. And then, because we assumed line 1 and we were able to conclude that line, we can get the implication. So you see, the only step now that we need to fill in here, and there might be several steps to fill, is this space here, the one that I marked with yellow line. So we're kind of squeezing this theorem, right? We know what the starting point of our proof is, we know how it ends, and we now need to fill the middle part. On this picture, what we want is to get delta as a conclusion out of 3 facts that have been given to us. That, and that. So these 3 correspond to the lines that are above the yellow dash line there, right? Let's actually identify which lines they are. So for every x there exists y, that's line 4. For every x beta, that's line 5. For every x, for every y, for every z gamma, that's line 3, right? And these lines, we've come to these lines through logical conclusion, so we don't have to check they're correct anymore. But we do have to check that we can get delta, which we can't assign a number to that line yet because we don't know how much lines we'll have to go after line 8. But we now want to check that delta can be logically concluded from 3, 4, and 5. And at this stage, we actually can abandon this graph, although we might have told ourselves, okay, we can still maybe scratch off this for all x and there exists y and so on, and come eventually down to alpha, beta, and gamma. The thing is that at this point we wouldn't know how, because how can you scratch off, for instance, this for all x? So in line 4, how would you be able to make a conclusion from this statement? This statement tells you that for every x something should be true, right? So to make a conclusion from it, you can start considering various different x's. Apply this that statement for some specific x and see what happens. But you don't know which x to choose. That will be hinted to you when you contemplate on what it takes to prove delta. That will suggest to us what value of x should we choose here so we get the thing we want. And the same for choosing a value for line 5 and choosing a value for line 3. I mean the values for x, y, z for line 3. So let's see how this is going to work out. I'm going to now zoom in. All the lines I'm going to put should appear in this space between line 8 and the next line with delta. At this point, we will have to recall what delta says, because that will guide us how to choose the appropriate values from the previous lines for these variables to apply these statements to those cases to give us something that we want. So delta says, and that will be immediately below the yellow part, right? Delta says x plus z equals y plus z implies x equals y. And now there are some few things we can scratch off here, right? How to get implication. How to get implication? Well, by assuming the left-hand side and concluding the right-hand side. So we can add one more ingredient to our assumptions. X plus z equals y plus z. And there will be another bracket here as well. And from there, from that assumption, we want to get to the conclusion that x equals y. You see, at this point, at this line, which is now line 9, right? Maybe I put the number on the other side. This is line 9. At line 9, before line 9, x, y, and z have already been introduced. They are some specific objects we're working with. They're actually general objects, but they were general objects when they were quantified with universal quantifier. But once we say let x be given, after that, x is something specific, although I don't know what it is. I can't assign a specific value to this x here. That will be wrong because I want my argument to be true for all possible x values. So I don't want to be specific here, neither here nor there. But I can assume they are something specific without me knowing exactly what they are. I hope this is not too confusing. So we are given some x, y, z such that x plus z equals y plus z. And from there, we want to get to the conclusion that x equals y. And by thinking about this hard, or maybe just using our usual intuition for numbers, we know that what we want to do is to subtract away z. But what allows us to subtract things away? Isn't it the alpha statement, namely the one line 4, that allows us to do things like that? The y there that exists for each x such that x plus y is 0, right? Let me zoom this back in. So in alpha, the y plays the role of minus x, right? And so if I could somehow add to both sides of this equation minus z, minus z will cancel out z, and I'll be left with x equals y. So this gives me a hint that I want to apply this line 4, in the case when x is z, right? Now, in order for me to do that, z already must be an object that we are given. But it is, because z was given at line 8. So now I can apply line 4 to z. In other words, take x equals z in line 4, but then drop the quantifier. So the way I'm going to write this out, and this is very important because this is now the first time where we're actually explaining what we're supposed to explain in this video, how to make conclusions from quantified statements. So what I will write out here, I will write out the exact copy of what appears here, but now in the place of x, I'll put z, and I'll drop the for all x. So then I'll have that exists, and now I have to be careful. If I write y here, this y will collide with that y, and so things might get confusing. So because the two y's have nothing to do with each other, remember this y was part of this quantified statement, and remember that the variable under a quantifier only has a meaning within the scope of the quantifier. So the scope of this quantifier and the scope of the other quantifier of this one are very different from each other. So the y's they appear in both of them have nothing to do with each other, okay? And so to emphasize that this y has nothing to do with that y, maybe I'd rather use a y prime here. So I know there exists a y prime such that alpha, and in place of x, I want to use z as I said, such that alpha zy prime is true. So this y prime will be like minus z, right? But I don't have y prime yet. at this point in line 10, I only know that it exists. How did we get line 10? We got line 10 by applying line 4. Line 4 says, whatever x you have, such a y exists such that alpha is true. Now, we picked a specific x for which we want to make use of this fact. We were told for every x, a y exists. So now I'm going to see what is that y for x being z, but not this x, right? So that's how I got this line 10 out of line 4. And what I want now is to start working with this y prime. And I can't, because remember the scope, I mean, this variable only has a meaning inside the scope of the quantifier. So I want to separate it from the quantifier. I want to eliminate this quantifier here. And I can't do that because now this is the other important point in this lecture. Well, the video, whatever it is. How to make a conclusion from existentially quantified statement. We are told the y prime exists. So what we can do in the next line, just write down alpha z y prime. Where alpha z y prime stands for this. So I will just write down z plus y prime equals 0. And maybe I will change the symbol further to remind me that the z prime is a companion of z. So what happened here? It's important to understand the difference between these two lines, line 10 and line 11. In line 10, we were told that there is a y prime, which later we're going to call z prime. We were told z has a companion. Line 11, in line 11, we've now introduced this companion into our proof. So now z prime became an object we can work with, something we can reuse later on, whereas y prime couldn't be reused later on from line 10 after line 10, because it was under the quantifier, and that was restricting its use just to line 10. It was restricting the use to line 10, and now by introducing the z prime as something we can work with, we can use z prime again and again and again, as long as we will be under the scope of the assumption, of line 9 assumption, in which it has been introduced. Okay, so let's continue. Now that we have the z prime, what we want to do is to add to both sides of this equality, we want to add z prime, right? So let's do this. X plus z prime equals y plus z plus z prime. And now we want to z and z prime to cancel each other out, but they can't cancel each other out. Remember, well, not remember, but look, I actually use brackets here. Why? Because, so what am I doing here now with line 12 actually? I think I was trying to go too fast here. So at line 9, we're told two things are equal, these two. And of course, if I take my plus operation, my plus functional symbol, and I apply it to this object and z prime, is the same as applying it to the same object and z prime. So it's clear these two things are equal, but it is important to keep these brackets, because the meaning of the whole reason why 12 follows from 9 is that we are keeping this as one entity, which is the same entity as the other one, as these entities are, and because they're the same entities, their sums will also be same entities. We can, however, switch around those brackets, which is what we will want to do in order for z and z prime to give us 0, using the other axiom. Well, it's not an axiom, it's something we've concluded previously, right? So gamma allows us to switch brackets around, you see? And the line where we have gamma is line 3. So we would have to apply line 3 in the case of x, z, and z prime instead of x, y, z. But that's fine, because we are told here that gamma x, y, z is true for all x, y, z, right? So in line 13, we can write x plus z plus z prime equals x plus z prime. That's thanks to line 3. Because line 3 tells us that we can swap around brackets for any 3 values, right? Okay, the same can be done for the other side, for the right-hand side of this equality. So we can also write y plus z. So we are applying now line 3 another time, right? One more time. Equals y plus z prime. And at this stage, we can make use of the fact of line 11 that z and z prime together add up to 0. So we'll have, maybe first I'm going to apply that fact to this part here. So we will have x plus z prime equals, I'm now replacing z plus z prime with 0. And the same for the other one, y plus z prime equals y plus 0. So this is our line 16. Now look what's happening here. We had this equal to that, right? But this first one is also equal to this, and that in turn is equal to that. So the left-hand side here is equal to x plus 0 actually. Whereas the right-hand side, similarly, the right-hand side is equal to firstly that, and that is equal to that. And of course, if one thing is equal to the other, then the other is equal to the third one, then the first one will be equal to the third one. And so we can, I mean, that's kind of basic rules of logic as far as equality is concerned. And so we will have that the right-hand side is equal to y plus 0 and the left-hand side is equal to x plus 0. But this is not good enough. We want x equal y in the end, right? I think now you know what needs to happen, right? So if we go back to our alpha, beta, and gamma, we will see that beta says that anything plus 0 is that thing back. So we can apply beta. And beta is available through line 5. If we apply line 5 in the case when this x here, for which beta is formulated in the statement for every x, beta x, so that x here, if we let that x be this one here, the one we're working with here, we will get that x plus 0 equals x. And now if we take line 5 and apply it again, but in this time we applied to the case of y in the place of x, we get y plus 0 equals y. And so if we keep track of this yellow part, the left-hand side, and keep track of the purple part, the right-hand side, we got that the left-hand side is x and the right-hand side is y. And so we can substitute those in the place of the left and the right-hand side in line 12 to get x equals y. So then x equals y would be our next line. And that's it. We arrived to where we wanted to arrive, right? From line 9, we managed to get to line 19. And the next line after that will be the one with delta, so that will be line 20. Then we have 21, 22, 23, and 24. So it turns out that this proof has 24 lines. What we are not doing in this series of videos is to identify exactly what the basic logical deduction rules are. And the reason why we're not doing this is that if we were to do this very, very precisely, it would be far too much to comprehend. Instead, what the goal is for you kind of, through these examples, for you to pick up for yourself, using your own intuition, what do we consider as basic logical rules? But of course, you will have to look at a number of different examples in order for you to fine-tune your intuition about that. And eventually, if you're really interested in this subject, you might want to sit down and for yourself write out all the rules that you think we ever used in these examples, and most likely there will be all the rules necessary. Another thing that we haven't done in this specific video is to number these lines. Sorry, no, we did do that. We numbered these lines, but what we haven't done is to explain, is to give an information on the proof, which line is based on which other lines. Like for example, when we wrote line 12, that was a conclusion based on just line 9, right? So since x plus z equals y plus z, we can say that x plus z prime equals y plus z prime. Of course, we first need to know that z prime is a valid object, so we'll probably also use line 11, which is the first line where z prime was introduced. And so we can say that for line 12, we used lines 9 and 11. And this way, every time we were explaining how we got each line from the previous lines, and we were pointing to some specific lines which were used to get those lines, they would appear in brackets here, just like we explained in the other video. Okay. What's the last step that remains? Well, maybe to copy this whole thing out, put it here and present it in a more sequential manner with all the previous part of the proof. But that I will leave to you. What I want us to do instead, not to take up too much time since we already had a 15-minute discussion, a bit more than that, I also want us to definitely do the following, which is to read the proof once we have finished writing it. And this is a very important step. If you don't read over what you've written, there is a big chance that a mistake slipped through. So it's very important, especially in mathematics, it's very important once you finish your proof to go back to it and read it over and reflect over it again and make sure that the proof convinces you of the truthfulness of the argument. And at this stage, you actually want to kind of forget how you got to the proof, because you want the proof to be informative enough to get you where you want to get. So if we start reading this proof, we look at the last line as a first step to see what we're supposed to prove. And then this last line has all these alphas, betas, and gammas, and deltas, and we have a reference here what they mean. So all of that is good. And then we start from the first line. Now in the first line, and after that we're going to just go in a sequence. We actually didn't have to look at the last line. So let's look at the first line. The first line introduces an assumption, right? No problem. We don't have to check here anything, because an assumption is something that need not be confirmed. There's no problem with that. Number 2 is a conclusion. And now we have to ask ourselves, okay, how did we get number 2? How can we get number 2? We can only use number 1 at this point. And then we notice that this part matches with that part. And so we got this number 2 because of the meaning of this conjunction symbol, right? Okay. Number 3, we get in a similar way because of the conjunction in line 1. So line 1 says one thing and the other thing are true. So both of them will be true separately. Line 4, after looking at it a little bit, we see, it validly follows from line 2. And you see at this point, it would have been so useful if we had made references which line follows from which other, so that when we read it over, we don't have to search for this anymore. Line 5 we get from line 2. You see, the process we're going through now is very different to the process we went through when we created the proof. At this point, we are trying to confirm that our proof is correct. We're no longer thinking of how to design the proof. The proof is already designed, it's already there. We're just checking that every next step logically follows from the previous ones. So we eventually reach line 6. In line 6, we're introducing an assumption, so we don't have to confirm anything there. Line 7, the same story. Line 8, it's an assumption, nothing to be confirmed. How do we know it's an assumption? The bracket opens up at that line. Then the next one is line 9. At line 9 we have an assumption again. Nothing to check there, right? Now let's look at line 10. That's no longer an assumption. We have to check line 10 does follow from the previous lines. And then we start searching for something that looks similar to this, and we notice that at line 4 we have something similar to this. And we also notice that what we've done here is that we've replaced the x with a y prime, with z actually, right? We replaced the x with a z, and we dropped the for all x. That is fine as long as z is a valid object. We can't introduce a new object out of nowhere, right? But if we look at before line 10, z is a valid object. We have z at line 8. In an assumption, but that's fine. That still means it's valid. So we can introduce a new object in an assumption. That's no problem with that, okay? Later on, line 21 will take care of the usefulness of this, right? Because of that introduction, we will say that, okay, so for every z something is true. So since z is a valid object up to this point, we can apply line 4 in the case when x is z, and so that's how we get line 10. Line 11, we now look at what alpha is, because otherwise we're stuck here, and alpha actually is x plus y equals 0, and so we see that now y prime now became z prime, and that's because, as we said before, line 10 tells us y prime exists, and in line 11 we actually are working with a y prime, which now we call z prime, just to be notationally more similar to z, because that's something that should cancel out with z. So that line 11 then is a valid conclusion of line 10, because line 10 tells us that such a thing must exist, and therefore in line 11 we can introduce the thing that we know must exist, so we can use it, and so it enters into a proof as an object that can be used later on. Let's look at line 12, and if I start comparing line 12 with the previous lines, I see there is some similarity with line 9. Indeed, line 9 tells me the left-hand sides of these summations are equal. And of course, z is equal to z prime is equal to z prime, so we can add the two things and still get them equal to each other. So line 12 is fine. Then let's go to line 13. In line 13, we are kind of rearranging the brackets, right? And so we notice that this bracket rearrangement happens in gamma, and on the other hand, on line 3, we have that gamma is true for every x, y, z, and so we know that we are fine with line 12. And the same goes for, sorry, not line 12, but line 13. And the same goes for line 14. Great, we've confirmed now line 13 and 14. Now with line 15, what we're doing here, we're replacing z plus z prime with 0, and that we can do because of line 11. So line 15 is a valid conclusion. Line 16, the same story. It follows also from line 11. Line 17, we're writing x plus 0 equals x. Where did we get that from? We don't see anywhere in the proof, but now let's recall that we had some abbreviations. Aha and beta gives an abbreviation. In fact, I think we skipped a few lines here because beta gives conjunction of two things and we only used one thing. So just like in moving from line 1 to line 2, when we isolate the things that are being conjuncted, we might have wanted to first write out this beta fully and then isolate the thing that we're actually going to use later. So, but eventually we will get that. So that's how we can get line 17. So you see, it was useful to go back to the proof because it turns out we actually skipped a step, right? let us actually complete this. How would we have done it if we hadn't skipped the step? So we wanted to apply beta in the case when x is x. So that comes from line 5, right? And so this would have given us x plus 0 equals x and 0 plus x equals x. And from this we can conclude x plus 0 equals x on its own. So it's just one line that we skipped here. And if I do want to insert that line, I can call this line 16.5. That will be a bit of a problem because it will my final number will no longer tell me how many lines does the proof have, or otherwise I can just renumber everything. So I can call this line 17 and then renumber everything. But let's not go into that. I think it's obvious what needs to be done there. Okay, so what about line 18? Same story. So another line is missing, right? So actually the line number has increased by 2 then. Okay, great. And then what about line 19? And so we have various equalities here, and we eventually are able to trace our way back to line 12. So x equals x plus 0 equals to that thing here in line 15, and then that thing here in line 13 is equal to that thing there, and that's equal to the left-hand side of line 12. So eventually we get x equals to the left-hand side of line 12, and y equals to the right-hand side of line 12. So we can substitute the left-hand side the left-hand side of line 12 can be replaced with x because they're equal, and the right-hand side of line 12 can be replaced with y because they're equal, and that's how we get line 19. And if we do this step by step, right, every time I got a chain of 2 equalities, I make the substitution, then of course we will have much more line numbers here to put. Okay, now we are at line 19. We confirmed everything, and now it's time to look at line 20. So line 20 says x plus z equals y plus z implies x equals 9. How do we know that? Well, at line 9 we assumed that the left hand side, and we concluded the right hand side, so we do know this. So we're fine with line 20. Line 21 says for every z something should be true, and indeed, in line 8 we propose to consider a certain z without any further restrictions on it, and we proved that thing to be true at line 20 under that assumption of line 8. So line 21 is justified as well. In a similar way, line 22 is justified, line 23 is justified, because each of them were obtained by first introducing some variable and then proving the thing we wanted to show for that variable to be a logical conclusion. Okay, so now we're at line 23, and final step is to get to line 24. And of course, that step is just the implication. We assume the left-hand side of the implication at line 1, and we managed to get to line 23. And so, therefore, we can write this implies that. So, we're done. Thanks for watching this video. Just to summarize overall what we did here, we learned in this video how to make conclusions from quantified statements, like when we were making conclusions from lines 3, 4, and 5. And also, that was for the universal quantifier. And at making conclusions from line 10, we saw how to make conclusion from the existential quantifier. And so I mean, that was the main goal of the video, but on top of that we also looked at other things because we chose quite a complicated example. We also now see in this example how to make implication as a conclusion, right? And how to conclude from a statement that has a conjunction in it. So these two other things were also covered in this video. And I guess that's it. And also we learn how to use substitution for deriving things that involve equality. And then I think that's what we did in this video. And that's the end of the video. Goodbye.